Now we'll discuss about Z transforms. So Z transforms is the second part of your unit 5. The first part was Laplace transform and the second part is Z transform. So Z transform, what is the definition of Z transform? Again, in Z transform also we have two different types: two-sided Z transform and one-sided Z transform. Right? Two-sided Z transform and one-sided Z transform. So two-sided Z transform is expressed as f of z, which is nothing but Z transform of f of n. Z transforms is for discrete time signals, right? If you look at all the transforms that we discussed so far, Fourier transform, that is a continuous time Fourier transform, is for continuous time signals, right? Discrete time Fourier transform was for discrete time signals. Laplace transform was for continuous time signals, right? And Z transforms is now for discrete time signals. So Laplace and continuous time Fourier transforms are for continuous time signals. Z transform and DTFT are for discrete time signals. So the definition of Z transform is f of z, which is equals to Z transform of f of n, the discrete time signal, that is expressed as, since it is discrete time, we'll have summation n equals to minus infinity to infinity f of n z to the power n, f of n z to the power minus n. So this is the definition for two-sided Z transform, right? This is the definition for two-sided Z transform. Now, if it is one-sided Z transform, if it is one-sided Z transform, there are two different types. Again, we can make this summation as for n equals to minus infinity to minus 1 and n equals to plus 0 to infinity. In this case, n equals to 0 to infinity means your f of n is defined only for positive values of n. That is, f of n is 0 for negative values of n, which means f of n is causal, right? If f of n is causal, then what happens? If f of n is causal here, I'll only have n equals to 0 to infinity. I'll only have n equals to 0 to infinity, like this. N equals to 0 to infinity, f of n z power minus n. This is one type of one-sided Z transform. That is, if f of n is causal. Now, if f of n is non-causal, that means f of n is 0 for n greater than or equal to 0. All these terms here becomes 0, and I'll only have minus infinity to minus 1. So the other type of one-sided Z transform is when f of n is non-causal. That is, f of z equals to summation minus infinite to minus 1 f of n z to the power minus n. So these are the different definitions for Z transforms. Symbolically, we write f of n, our discrete time signal, has the Z transform f of z. Very similar to all other symbolic notations, the time domain signal will have the transform and the whatever transform is on the right hand side, right? So my time domain signal is f of n, and it has a Z transform of f of z. Now we look at advantages of Z transform. So advantage of Z transforms: it exists for most signals for which DTFT does not exist, right? When we discussed about DTFT, we have discussed that it must be absolutely integrable for the signal to have a DTFT. The signal must be absolutely summable, not integrable, absolutely summable for DTFT to exist. For even such signals where we cannot find a DTFT, we can find a Z transform, just like Laplace transform. There are some signals for which we cannot find Fourier transform. right? Continuous time Fourier transform. But even for those signals, we can find a Laplace transform. Similarly, there are some signals for which we cannot find DTFT. Even for those signals, we can find Z transform. Even for those signals, we can find Z transform. And then the second advantage is difference equations of a system can be converted into linear algebraic equations, and analysis of LTI systems becomes very easy. Similar to Laplace transforms, there we have differential equations. The system was defined in terms of differential equations, and we converted those differential equations into linear algebraic equations to analyze the systems easily. Now we are going to use difference equations in Z transform, right? Since Z transform is for discrete signals, discrete time signals, we will use difference equations to describe a system, and these difference equations can be easily converted into linear algebraic equations, and the analysis of the system becomes very simple using Z transforms. And then convolution in time domain becomes multiplication frequency domain. This is an advantage of almost all for all transforms. Any transform you take, this is a very big advantage. Convolution in time domain is multiplication in frequency domain, or in this case the Z domain, in this case the Z domain, right? It is easy to do multiplication than convolution. That is what this advantage states. The last advantage is DTFT is applied only for stable systems, whereas Z transform can be applied to analyze unstable systems as well. So DTFT we can apply only for stable systems, right? That was the condition for DTFT. What was the condition? The given signal must be absolutely summable, right? That is, it must be absolutely stable. Only for that, in such cases, we can apply DTFT. Whereas Z transform, we can use it to analyze both stable as well as unstable systems. Limitations of Z transforms is similar to that of one of the limitations of Laplace transform. What was the one limitation of Laplace transform? There was no frequency and phase information from Laplace transform. Same thing, the frequency domain response. Frequency domain response means, or frequency response means, magnitude and phase. These magnitude and phase characteristics of the time domain signal cannot be achieved or plotted using Z transforms. This is the only limitation for Z transform. Now, since both DTFT and Z transforms are applied for discrete time signals, we can find a relation between both the transforms. We can find a relation between Z transform and DTFT. Now, what is the formula for Z transform? It is x of z, or for f of n, the Z transform is denoted by f of z, right? It is denoted by f of z. Now, f of z equals to summation n is equals to minus infinity to plus infinity f of n into z to the power minus n. Now, z is a complex variable, right? Z is a complex variable. Now, z, I am going to write it in polar form. Z, I am going to write it in polar form. R into e power j omega, where r is the radius and omega is the angular frequency, right? Z equals to r into e power j omega. That is the polar form. So if I substitute that here, now I can write it as r power minus n and e power minus j omega n. I am combining the terms f of n and r power minus n. Now if you look at this, what is this? If you consider this as my function, so summation n is equals to minus infinity to infinity my function into e power minus j omega n. This is nothing but DTFT of my function, discrete time Fourier transform of my function. So discrete time Fourier transform of f of n into r to the power n. So what can we say? F of z is nothing but f of z at f of z is nothing but DTFT of f of n r power minus n, f of n r to the power minus n. Now when I substitute r is equals to 1, when I substitute r is equals to 1, what will happen to z? Z will become e power j omega. Z will become e power j omega. Then my DTFT is going to become, if I substitute r is equals to 1 in this equation, what happens? F of n into r to the power minus n is nothing but f of n. And then I have e power minus j omega n. So this is nothing but DTFT of f of n. It is same as DTFT of f of n, that is denoted by f of e power j omega. Now what is the relation between DTFT and Z transform? DTFT of f of n, DTFT of f of n is nothing but f of z, f of z. This is nothing but DTFT of f of n, right? So DTFT of f of n is nothing but f of z when z is equals to e power j omega. DTFT of f of n is equals to f of z when z is equals to e power j omega. So this is the relation between Z transform and discrete time Fourier transform.